Hi guys.
Hi.
Hi.
The due date for our dynamic assignment is very soon already. What topic do you guys think that we should do?
Actually, I have an idea because like recently I just saw a video of someone playing bowling, so maybe we can use this as our title. What do you guys think?
Speaking of bowling, guys, my sister is actually a bowling player. So before the pandemic, she has been very active participating in bowling tournaments. I've been to quite a few of them, and I also managed to record some of videos of her playing bowling. So yeah, maybe we can use some of the videos for this assignment, and from there maybe we analyze the motion of the bowling ball. So what do you guys think?
I think it sounds great.
Yeah, I agree with that idea. I'm okay with that.
Okay. So let's proceed with bowling for our assignment.
Okay.
Sure.
Hi, I'm Adriana. So in this video, my friends and I will walk you through on how to solve problems relating to the motion of a bowling ball. So here is the video sections, including all the three LOs that we are going to focus on this example. So before that, let's take a look at this short video of my sister during her bowling tournament last year. Right, if we want to discuss regarding the motion, it can be quite complicated sometimes, but as you may observe, when she launches the ball, it first appears to slide, and only then it begins to rotate more and more quickly until at last it rolls without slipping. So from here we can divide the motion into two segments, which are the sliding phase and also the rolling phase. In the next section, we are going to analyze both of these phases to calculate on how long does the ball slide and when does the ball starts to pure rolling. So without further ado, let's find out.
Hi everyone, my name is Choong Hui with metric number U2003895. I'm going to proceed with LO1, which is determine the problem of the related motion. So we have our bowler here, and she's going to throw the bowling ball with an initial velocity. We are going to assume that the ball doesn't have any angular velocity, so here is the sliding motion of the ball, while here is the rolling motion of the ball. Today we are going to determine 4 problems, which is first, calculate the acceleration of the ball. Second, calculate the angular acceleration of the ball. Third, calculate the distance of the sliding motion, and finally, calculate the time of the sliding motion.
Hi, my name is Ooi Hui Luan, and my metric number is U2003946. And now I'll be explaining the LO2, which is solve problems of accelerating rigid bodies in 2D. First of all, I need to identify the forces and all the possible factors that affect the accelerating rigid bodies, and show by construct the free body diagram and kinetic diagram. And lastly, I need to state all the assumptions. Normal reaction force act on the bowling, and also the weight, and also the frictional force of the surface of the bowling lane. And this is the free body diagram. Assumptions that I made are the angular velocity is equal to 0 radian per second, and the initial velocity is 5 meter per second, and the coefficient of kinetic friction is 0.08, which is very small, and the radius of the bowling is 10 cm. The mass of the bowling is 8 kg, and the length of the bowling lane is 50 meters.
So I'm going to resolve all forces into x and y axis. So for the x-axis, summation of fx equals to ma. So x-axis we only have a frictional force. So in the negative direction, so we have negative f equals to ma. For the y-axis, we have summation of fy equals to 0. We only have the normal force and the weight for the y-axis. So n minus w equals to 0, where n equals to mg because weight equals to mg. So as we all know, the frictional force equals to the coefficient of friction times normal force. When we substitute n equals to mg inside the equation, f equals to coefficient of friction times mg. So when we cancel off the m, the mass, we will get the formula for linear acceleration, which is a equals to negative coefficient of friction times g. Next, we'll proceed with Newton's second law of rotation, which is summation of torque equals to I times alpha, where I equals to the moment of inertia and alpha is the angular acceleration. So summation of torque, we add up the torque of the frictional force, torque of the normal force, and the torque of the weight. So the formula of torque equals to Fr sine theta. So we can actually cancel the torque for the weight because the distance to the pivot is 0. Okay, so when we look at the torque for the normal force, although there are certain distance to the pivot, but because the angle is either 0 or 180, so we can also cancel off the torque for the normal force. So we are left with the torque of the frictional force, where the torque of the frictional force, the angle to the pivot is 90 degrees, sine 90 degrees equals to 1, so we only left with the frictional force times R equals to moment of inertia equals to 2 over 5 mass times radius square times alpha. So we cancel off the mass, cancel off the R, we are left with angular acceleration equals to 5 over 2 times the coefficient of friction times G over R. So finally, we are left with two equations, which is the linear acceleration, which is A equals to negative coefficient of friction times G, and the angular acceleration is equals to 5 over 2 times U coefficient of friction times G over R. That's all from me. Thank you.
Hi, my name is Hui Yee. Now I'm going to present LO3, which is analyzing kinematics and kinetics problems in particles. So these are the two equations that we obtained from LO2, one for the linear acceleration while the other is for angular acceleration. So our first problem is to find the acceleration of the ball. So by using this equation and substituting k equals to 0.08 and g equals to 9.81, we'll get negative 0.7848. And the second problem is to find the angular velocity of the ball. So by using this equation and substituting r equals to 0.1 m, we'll get 19.62. Okay, for the third equation, we need to find how long is the time taken for the sliding motion here. So first, we apply the constant acceleration equations for motion in a straight line, which is v equals to v0 plus at. While for the angular motion, we use omega equals to omega naught plus alpha t. And then after substituting this equation into the constant acceleration equation, we will get these two final equations that will be used for the calculations later. So now we look at here. As we know, the ball, after the ball is done sliding, it will not slide anymore and it will start to roll. So here at this point is where the v equals to r omega. So by using these two equations, we will get v0 minus mu kgt equals to r times with 5 over 2 times with mu kg over r times with t. So after some calculations and substitution of the value, we'll get t equals to 1.82 seconds. So we know that at t equals to 0 to 1.82 second, the ball is sliding, and after 1.82 second, the ball is actually start to roll. Okay, so the fourth question is to find the distance of the sliding motion. So we apply the equation s equals to v0 t plus 1 over 2 at squared. By substituting the value inside, we'll get s equals to 7.8 meter. So this 7.8 meter is actually the distance that the ball sliding. After knowing the time for the ball to start pure rolling, which is 1.82 seconds, we can also find the velocity of the ball at this point. So we take v equals to v0 plus at, and then we substitute the values. T equals to 1.82 inside this equation, and v0 is the 5 meter per second. So we'll get the velocity, the phantom velocity at this point will be 3.57 meter per second. Next, we move on to solve the conservation of momentum and energy loss. So as we know, when the bowling ball strikes the pin, collision happens. So by using the equation m1u1 plus m2u2 equals to m1v1 plus m2v2, we are able to find out the final velocity of the bowling ball and the pin. Okay, so first we need to determine the initial velocity of the bowling ball before striking the pins. So by using the equation v square equals to v0 square plus 2as, we can find out the initial velocity of the bowling ball. But in this equation, the initial velocity of the bowling ball before striking the pin will be the final velocity, and the initial velocity will be the velocity that we get from the previous question. So as we know that the length of the lane we assume is 18 meter, and then the sliding motion take 7.8 meter. So we can find the distance for rolling motion is equals to 15 minus 7.8, which is 7.2. So we substitute the value of the rolling distance and also the V0 equals to 3.57 into the equation, we can get the initial velocity of the bowling ball, which is 1.2 meter per second. Okay, after knowing the initial velocity of the bowling ball, which is 1.2 meter per second, we can start to solve the problems. And we know that the initial velocity of the pins is equals to 0, and the mass of the bowling ball is 8 kg, while the mass of the pin for one pin is 1.6 kg. So from here, M1U1 plus M2U2 equals to M1 plus M2 times V. This V is the this velocity is the velocity of bowling ball and pins. Since after the collision, the bowling ball will go along with the pin, so they have the same velocity. So after substituting the value, we get the final velocity of bowling ball and pin is equal to 1 meter per second. Now we calculate the kinetic energy before collision and after collision to find out whether the kinetic energy is conserved or not. So before collision, the kinetic energy for bowling ball and the pin is 5.76 joule. And then after collision, the total kinetic energy becomes 4.8 joule. So from here, we can see that the total kinetic energy before collision is not equals to the total kinetic energy after collision. The energy loss is 5.76 joule minus 4.8 joule equals to 0.96 joule. The energy loss is because the energy is transformed to other form of energy such as sound energy.
So to end the video, here is her with Shadin Zulkifli, a Malaysian professional 10-pin bowler. And to conclude the video, we could see how important it is for bowlers to recognize and know their ball's movement down the lane, as this helps them to deal and adapt to different oiling patterns, especially during tournaments, so that they could hit the pocket at a significant angle to gain a strike. That is all from us. Thank you.